Okay, so kind of leaving off where we left off, we're going to talk about the existence of a limit. And so not all limits exist. Okay, so I'm going to read this existence of a limit theorem here. If f is a function and c and l are real numbers, then the limit as x approaches c of f of x is equal to L if and only if the left and right hand limits exist and are equal to L. So what this is saying is that the left hand limit and the right hand limit have to both approach the same number for the limit to exist. Okay, so let me write out the notation here. The limit as x approaches c, right, from the left, there's just a negative number here on f of x is equal to L. And the limit as x approaches c from the right, okay, so this plus just means it's approaching from the right, of f of x is also equal to L, okay? So in order for the limit to exist, right, this value right here, the left-hand limit, we'll call it LHL, left-hand limit, has to equal RHL, okay? And this is your right-hand limit. They both have to equal the same number, whatever L is, okay? Again, this is your left-hand limit as x approaches c from the left, and this is your right-hand limit as x approaches c from the right, okay? Both these numbers have to be the same for it to exist. All right, so we're going to talk about 3 cases in which the limit does not exist. And so if you flip to your notes, right, I'm going to give you 3 cases where the limit does not exist. Okay, so we're going to start with case 3, 2, and then we're going to go backwards to 1. So if you take a look at this graph, right, sine of pi over x, and I don't expect you to graph this by hand, nor does, the AP College Board expect you to do it by hand. So here's your graph, and if I ask you what is the limit as x approaches 0, right, it looks like the y value is oscillating between 1, right, and negative 1, right? It doesn't really approach a specific number, and you probably need a microscope to see what the heck is really going on, at 0 or close to 0. And so this type of function we call an oscillating between values, okay? So an oscillating function between, it doesn't have to be 1 and negative 1, right? It could be anything. And the only way to know that, right, is if you look at the graph, right? The y value is just bouncing up and down between 1 and negative 1 as x approaches 0 from the left and from the right, okay? So this type of function, the limit does not exist. So if I ask you what is the limit as x approaches 0 of sine of pi x, right? You look at the graph, okay, pi over x is in the argument. You just say does not exist, DNE. Okay, why? Because the y value is oscillating between 2 values, okay? All right, now here's another case. If you look at the graph of 1 over x to the 4th, right, the limit as x approaches 0, what is that? Well, on the left hand, right, as x approaches 0 from the left, this is approaching positive infinity. On the right hand side, as x approaches 0 from the right, the y value, of course, is also approaching positive infinity, right? And so actually this, if we want to use our notation, the limit as x approaches 0 from the left of f of x, right, you could technically say it's infinity. And the limit as x approaches 0 from the right of f of x, that's also infinity. Now you're like, well, the limit as x approaches 0 from the left is infinity. The limit as x approaches 0 from the right is infinity. Don't they approach the same number? Well, that's the key, right? If you go back to the informal definition, if f of x gets close to some number L, okay, as x approaches c from the left and the right, the limit of f of x as x approaches c is L. So this number, right, I mean, this guy right here has to approach some number, right? So infinity is technically not a number. And so in this case, we say does not exist. Okay. Do the left and right hand limits exist? We can talk about this in further detail, but I would say yes, the left and the right hand limits exist, but the actual limit itself does not exist. Okay, so again, it has to approach some number. Infinity is not a number. All right, so that's another case where it does not exist. The last example right here is case number 1. And this one right here, I'm going to show this problem to you algebraically, okay? So I expect you to know how to graph this by hand. And so let's take a look. So recall the definition of your absolute value, right? And if you rewrite this as a piecewise function, right, f of x is just going to equal positive x for x is greater than or equal to 0 and negative x for x is less than 0, okay? And so if we look at our function right here, this is our f of x, right? F of x is equal to the absolute value of x plus 1 over x plus 1. Okay, so right now I'm going to write this, rewrite as a piecewise. All right, well, how do I rewrite that as a piecewise? Use this definition, right? It says that basically I drop the absolute value symbol, x plus 1 over x plus 1, and then I set the argument's whatever's in here, right? Greater than or equal to 0. The argument is this. So I made a mistake there. Set it greater than or equal to 0. And then I also have negative of this, right? So the negative of this with the absolute value dropped is this. And then I set the argument less than 0. Okay, so again, whatever's in here is basically what's inside the absolute value symbol. Okay, so this will define my domain. Okay, now there's another trick on this problem, right? After I rewrite this as a piecewise function, well, believe it or not, this is actually a Math 2 skill. It's in the Math 2 textbook, but regardless, let's finish this problem. There's another trick that you gotta really think about here. When these two guys cancel out right here, right, it cancels out to basically positive 1. Remember, when this cancels out, right, this implies that there's a hole at x plus 1 is equal to 0, right? Remember when you simplify your rational function, right? Whenever you canceled out, you set that canceling factor equal to 0 and you solve for x. There's a hole at x is equal to negative 1. Now, if there's a hole at x is equal to negative 1, right, this means I have to change this, right? Because if I solve for x, right, this will be x is greater than or equal to negative 1. I can't have it to equal, so I have to get rid of this. Okay, so this actually has to be gotten rid of, right? Because it can't equal negative 1, right? Because there's a hole at negative 1. Remember, if I plug in f of negative 1 right now, you would say undefined, right? F of negative 1 is equal to undefined. And so you can't have an equal sign there, even though the original equal sign was from the definition of absolute value, okay? So if you solve for this, right, x is greater than negative 1. This cancels out, right? Also equal to negative 1. Remember, there's a negative here. That's from the definition. And this is x is less than negative 1. Okay, so now you have the piecewise function, right? And you can graph this without much difficulty. So let's translate this to the graph. So the graph will look something like this. There's 1, negative 1, and negative 1, okay? So for x is less than negative 1, I have the value of 1, right? X is less than negative 1 is going this way. And this is an open circle. I have a value of positive 1. and x is less than negative 1, sorry, I think I graphed this wrong. For x is greater than negative 1, it's positive 1. So greater than negative 1 is positive 1. And for x is less than negative 1, right, it's negative 1. So the graph will look something like this. Okay? All right, so there's my graph, right? Now, I just defined left-hand limit and right-hand limit with you, right? In order for the limit to exist, the left-hand limit and the right-hand limit have to both be the same. So if I ask you, what is the limit as x approaches 1, negative 1, I should say, from the left, right? This is your LHO, right, from the left. X approaches negative 1 from the left. Well, it looks like it's getting close to negative 1, right? And if I ask you, what is the limit as x approaches negative 1 from the right of f of x? Well, from the right, as x approaches negative 1 from the right, it looks like it's approaching positive 1. Notice your RHL and your LHL don't equal, right? And so for case number 1, when your left-hand limit does not equal your right-hand limit, right? Then this limit does not exist. Okay, so going back to our beginning here, right? Both of these numbers have to be the same for the limit to exist. Okay, so case number 1, I wanted to say for the end because a lot of this absolute value algebra stuff is quite important because you'll see these problems in your calculus textbook in addition to, I believe, your math analysis homework as well. Okay. So case number 1, when the left-hand limit and the right-hand limit don't exist, right? One guy's approaching negative 1, another guy's approaching positive 1. These two numbers aren't the same. Case number 2, when you have, basically, they call this an unbounded function, right? It doesn't approach a specific number, and infinity is technically not a number. And case number 3 is when it's oscillating between a couple of values. Those are the instances when the limit does not exist. All right, so let's take a look at some graphs right here. Use the graph to find the limit if it exists. So basically this is way number 2 in finding limits. So the nice thing is the graph's already there. We kind of just have to take a look. Okay, so what's the limit as x approaches 0? Well, as x approaches 0 from the left, right? This function, what does the y value get close to? It looks like the y value is getting close to 1 on the left, and as I'm approaching x's from 0 from the right, the y value is also getting close to 1. So the answer in this case is just 1. Okay, so you just take a look at the graph. Again, you have another function right here. The question is the limit as x approaches negative 3 of this function, which is already graphed. Okay, so negative 3 is right here on my graph. And as I'm approaching negative 3 from the left, it looks like it's getting, this is 1/2 of this. This was negative 0.25. It looks like it's getting close to negative 1/4. And as x approaches negative 3 from the right, it looks like it's also getting close to negative 0.25. Okay, so you could say this is negative 1/4 just based on the graph. Okay, so that's just reading the graph. And as I said, if you understand the concept, it's not super difficult. All right, let's take a look at one more problem here, and then we'll move on to a different section. Find the limit as x approaches pi of cosecant. Now, as x approaches pi from the left-hand side, right, it looks like it's going to positive infinity. As x approaches pi from the right-hand side, though f of x looks like it's approaching negative infinity. Whether or not this approaches positive infinity or negative infinity, we know infinity is technically not a number. And so this one right here is just does not exist. Okay, so this would be case number 2 in your limits that don't exist. It's an unbounded function.